Right, the nonlinear term, sometimes called the advected term or the inertial term, which is u dot grad u. And it's the only nonlinear term in the Navier-Stokes equation, so it's really the only one capable of mode mixing or changing the frequency or spatial content. All right, so number 2, somebody want to volunteer that? Oh, it's okay. Huh? Go ahead. Well, that's not technically false. It's not completely true. Anybody else have another suggestion? Okay, so I'll give you a hint. The inertial waves are only present when you have rapid rotation. So what additional forces occur with rapid rotation? Right. Okay. So by consensus, then we've arrived at the answer. So but pressure does balance Coriolis. So in fact, if the time derivative Coriolis and pressure terms are dominant, you get these waves. So
wait, aren't ocean waves also considered to be inertial waves?
Okay, so there are many types of ocean waves. Are you talking about the waves on the surface of the ocean?
Yeah.
Okay, so those are called gravity waves, but of course they're not general relativity gravity waves.
Right.
They're a buoyancy restored wave. They're called, well, the long ones are gravity waves. The short ones are capillary waves, and the crossover is about a centimeter between those two restoring forces, centimeter wavelength, give or take. Okay, so anyone except Greg want to answer number 3? Yeah, please.
It's the reference frame that moves with the particle.
Right, moves with the particle, or even in the absence of particles, moving with a parcel of fluid that's just going with the flow, if you will. And of course, that's a interesting alternate reference frame to fixed in inertial coordinates, or in the case of a rotating experiment, we're often the rotating frame, but that's also a type of Eulerian, I suppose, reference frame moving with the overall rotation of the apparatus. All right, last but not least, what is K41 and what is its main then hypothesis that it advances? How does epsilon depend on U and L?
U cubed over L.
Right, U cubed over L, right. So the main result of K41 is that the energy dissipation per unit mass does not depend on viscosity and only depends on velocity and length scale. There's only one combination of velocity and length scale that will give you the units of epsilon, which are meters squared per second cubed, and that's U cubed over L. And it's a wildly successful theory, actually, and underlies the starting point of much of what Bruno just talked about, I would say. It's sort of the initial guess for how all these various scalings are, and of course things are more complicated than just the first. Okay, so let's see. I think actually I'm going to turn off we'll do tails of caution, which I'm embarrassed to say I just forgot and left off last time, but they're probably useful enough to talk about that. Okay, so this is just a portion of the last lecture that I missed. And these are the sorts of things that don't always make it into the literature. Well, no, actually, I probably want this slide on there. The sort of things that don't make it into the literature necessarily because people don't always tell you how things fail. And in fact, if they're trying to advance how good their thing is, they may not tell you what the hardest thing is, the hardest obstacle they face. They may actually try to downplay that, worrying that the referees will jump on it and strangle them. But because I would like you to do well, you should hear about a few of these. So one of the tales of caution is that a very frequently used approximation in measurements is Taylor's hypothesis. And a lot of the historical data about turbulence was using Taylor's hypothesis, which actually is that if you go to measure something, it is much easier to measure something, let's just say v sub x, for instance, as a function of time, because it's just much more easy to build an instrument that sits stationary and then gives you a time record, which then historically would have gone on to a tape recorder or a, what do they call those plotters? Yeah, plotter with a scrolling piece of paper. Now, of course, we just spool them into a computer after acquiring it. So, but Taylor's hypothesis is that you can infer then what v of x does if there's a big velocity that's carrying things past you. So let's say there's some big v of y, then we can just say, well, this is really approximately v of x, x over v of y. And so really then the underlying assumption is that things are going so fast by you, they're not changing. They're kind of frozen in space. And so you can interpret your time series as if it's a spatial series. And almost all the early measurements of the k to the minus 5/3 spectra were not in fact k to the minus 5/3 spectra, they were f to the minus 5/3 spectra, and they used Taylor's hypothesis then to try to infer what was going on otherwise. And this is not, this is approximately true sometimes if you have a large mean background velocity, but be cautious. And it's good to ask people what they did, and sometimes don't always explicitly state that they had a time signal they're interpreting as a spatial state. Okay, questions, comments about Taylor's hypothesis? Okay, so the next cautionary note has to do with how much data. And we heard quite a bit this week about statistics of what I'll call delta U sub r, which is going to be defined to be u of x at some x plus r minus u x r. And then people compute these structure functions, which are various moments of this delta u of r to the nth power. And carrying on with power law quizzing, and they say that these are scaling like some power of r to some, let's say, zeta sub n. And so the issue is that these different orders of n are not equally easy to measure. And measuring n equals 1 or 2, it's pretty straightforward. But if you want to know what n equals 6 is, I already start getting a little nervous. If you want to know what n equals 10 is, I start questioning your sanity. And the problem is that what this is a moment of a probability distribution. So let's try to draw that schematic here. So there's a probability distribution, PR of delta U R, and well, it could actually be centered on 0. And if we actually, let me just do log that versus delta U sub R, and that will have some shape. And these tails are either exponential or Gaussian, or there's something usually falling exponentially, so that 10 sigma or 20 sigma events basically don't happen in delta U sub R, maybe unlike the acceleration. But when you go to take that, what you're doing is you're going to take this probability distribution, you're going to multiply it by delta U sub R to the 4th, let's say. So what that does, of course, is that it zeroes you out where delta U sub R is 0, because you multiply by delta U to some power. And so then unfortunately it's on a log plot, but a log plot then, the thing that you're actually then computing is an integral of this thing, right? So this is delta U sub R to the n, let's say, times PR of delta U sub R, and if you integrate that, you get that answer, right? It's a moment of that probability distribution. But the problem is that power goes up, you're sampling further and further out in the tails, so you're sampling actually very rare events, okay? And I guess I had thought up to this week that the answer to how much data do you need for this was 10 to the n. Okay, but I guess Nigel told me that was false, and I generally tend to believe Nigel when he tells me things are false. He says that it's actually something more like n factorial. So it's actually worse than exponential when you go to high n. Okay, so I've actually computed some of these moments in some turbulence experiments. What?
I mean, that depends totally on the functional form of your tail.
Well, yes, that's right. Right, so I could probably concoct models that would have either one of those, depending on the functional form.
But if you're trying to measure it, then
Either way, okay, you're exponentially screwed when you try to measure higher moments. Okay, you can quote me on that. and actually, and you probably heard me then question some of the speakers as to A, do you believe this 10th order moment, and B, does this have anything to do with anything we want to predict in nature? And I think the answer is usually no, I don't believe it, nor does it have anything to do with nature. So just be cautious about higher moments. Do you think that's unfair, Greg?
I would say it a little differently. I don't think
Well, I swear more than you do, I
there's
think.
any physics that I've ever gotten beyond n equals 5.
Okay.
But by the time you go out to n equals 5, you can tell the intermittency scaling pretty well.
And you can tell you things are different than something. Right. Okay. So that was Taylor of caution number 2. All right. Okay. Questions, comments about that? Okay. Taylor of caution number 3. Gradients. Derivatives. Oh my. if you tried to take the derivative of any experimental quantity, for instance, trying to measure the gradients of the quantities, trying to measure the acceleration of the quantities, that is problematic in general. It's difficult, it's hard. It can be done, but only with caution. And the more derivatives you take, the more problematic it is. Okay? And I can easily show you why. If we think of the power spectra of some measurable quantity, let's say velocity. And so this is actually not the Fourier spectra, but it's square modulus, so it's the power. So if we think about the power spectra for the velocity, let's say it's a function of frequency, since that's usually how it's measured, I might have a k to the minus 5/3 range, and you saw all sorts of plots like that. What those plots didn't show you is what the data's power spectra actually looked like. Because were they to have shown you an honest power spectra, they would have shown you that at some point you reach an instrumental noise floor, which is often white. White noise just means flat in Fourier spectra or power spectra. Because every instrument has noise. Right? There is no noise-free instrument. That's always at some level. It's usually white because it's IID noise. And it's unavoidable. And actually, if they were really honest, you would probably also see out in here at least one peak at 60 hertz. Because it's extremely hard to do any measurement in the laboratory that doesn't end up giving you a 60 hertz peak. Although, obviously, that's a country-specific problem, which peak you might end up with. So where's the 50 hertz? In Britain? Okay, yeah. So, but it's the same problem. I'm sure this must cause some play in the UK too. It's not. Not specific to the frequency. So the problem is then, is if I go to take the derivative of my velocity, which I can do 4 differences, for instance, is the naive thing to do. Of course, a derivative in Fourier space is equivalent to multiplying the Fourier spectra by I omega. Okay, that's just a simple nature of the e to the I omega t. When you take this derivative, you get a factor I omega in front. So in the power spectra, then, you actually get a factor of omega squared in the power spectra, multiplied on top of your power spectra. So now, okay, so what I'm going to do then is I'm going to plot SV dot versus F, and actually, let me do that in another color. SV dot F, and that's simply related to this by a factor of F squared, so we can sort of schematically do that. So instead of a k to the minus 5/3 slope here, I will have a plus 2/3 slope, right? No, plus 1/3 slope, I'm sorry. Okay, it's a plus 1/3 slope. So I'm going to have a slowly rising signal here with a 1/3 slope until I reach this point, and then this flat noise will suddenly become an F squared dependence. Okay? So the power spectra of the time derivative of the signal, if you look at where most of the power is in the instrumental noise. Okay. Now, this is the underlying problem of taking derivatives of any sort, is that you magnify noise. And the more derivatives you take, the more you magnify noise. And there probably have been many, many papers in the published literature you could find if you went looking for them, where people spent a lot of time analyzing their noise signal, thinking it was a derivative of some more fundamental quantity. So be cautious about that. Now there are ways around that, and most experimentalists become experts in the ways around that. The most common way around it is to use least squares, to fit a line to multiple points in your data and use the slope of that fit line as an approximate to your slope. And you even can have a fairly good notion of at what time scale range to do your fit over, because you can look at the crossover between your actual data and your noise data, and just then fit through your noise data, and that, you can do better that way, for sure. Okay, so in fact, in trying to measure derivatives, people end up using Taylor series approximations that slide in time, and they fit then a lower Taylor series model to their data, and use the results of that fit rather than forward difference is a bad idea, I guess. But even center difference, usually for most data, is going to give you a lot of problems. Okay, questions, comments? Yeah, please.
Do you usually know what the noise is going to be from the instrument itself, like from the way it's calibrated or things like that?
Oh, so it's not a calibration thing, it's a background noise, it's shock noise of some sort, usually. Well, usually you can just see it in the power spectra of your data, but there are specs you might get from them, but it depends then, so we scratch build a lot of electronics in our lab, and so then the performance of the instrument is going to depend a lot on your technique of scratch building your electronics. And there's an entire PhD's worth of information to know to get that right. But it's more or less low noise techniques in electronics they're slowly spread, not through the literature. Yeah, please.
Well, rather than trying to predict it, you could just measure it. typically, right?
Yeah, that's what.
Absolutely. Yeah, and you can do that when your system's quiet, so you can actually, you can turn off your flow in most cases and then just sit there and say, well, what's the noise coming out of it?
I was just curious how well the instruments work.
Yeah, it's a huge variation, right. Okay, other questions? Yeah,
I
please.
just had a comment related to this. So the natural solution is to do some kind of fitting to smooth over the noise, but you also have to be very careful because you can always make your data smoother by smoothing more and more, and you're starting to remove your signal. And so then that process
Filtering, yeah.
of when you're removing signal and when you're removing noise is impossible to do rigorously. And I spent a couple of years in my PhD figuring out where that fell for those two derivatives we were trying to take from the position data.
Yeah. So, okay. Okay, so actually, I think that we have only 2 or small bits of cautionary notes, and then we can press on to what was intended. So the outline's over there, if it's legible. So the last thing, or no, penultimate thing, is don't get distracted. By small details that are essentially non-scientific. And so the problem is then, this is a question of research maturity. You have to gauge what's important. And of course, this is extremely difficult to do. But let me tell you a story to illustrate this point. So there's a graduate student, at the same time I was a graduate student, had an experiment, fully functional experiment, that the temperatures of the experiment drifted some, over about a 2-degree window. And he became very fixated on temperature control. We're talking like almost a year's worth of fixation on temperature control. Never taken any data of his experiment because he didn't think it was worthwhile to take data when his temperature control was not fixed. And so the problem then is he had no data in hand, and neither could he fix his temperature control problems to his satisfaction. And after about a year more of this, his advisor fired him. Okay? Because it was clear that he was incapable of taking data and was incapable of judging what was important in the experiment and not. Okay? So think about what it is you're trying to fix, and think about whether or not at any given point you can get some preliminary data. Okay? Because in my experience, the problem you think you're going to have in your science is not necessarily the problem you're going to have in your science. And so unless you try to get some data, you may not have uncovered what your real problems are. Greg, do you think that's a reasonable?
That's a wonderful bit of advice. Very hard to implement in practice, but it's...
Well, and so what I found is if your goal is very high quality data, take some data, find out what's wrong with it, make some improvements. Take some more data, find out what's wrong with it, make some improvements. And an iterative process then. But at any point then, if you had to, you could just call it quits, right? Because you got your data, right? And so you would not be left empty-handed, right? If you need to suddenly move to Korea because of a family emergency and you've not taken any data, it's going to be hard for you to get your degree in short order, right? Or whatever emergency might arise. So it's just good to, okay. Data in the hands worth 2 in the bush? Okay, that was bad, sorry. All right, so the final cautionary note is probably the most difficult to address because we're all only human, okay? And the final cautionary note is that presumptions cloud observation. If you go into a scientific project being absolutely sure you're going to get power laws, then by God, your chance of publishing power laws are near 100%. Independent of the underlying physics of your problem, unfortunately. Because all you have to do is narrow your range over which you're fitting your function, and if it's differentiable, you've got a power law. Declare victory. But that's not good for science, honestly. Now, I don't criticize power laws, but there are a lot of power laws in things we observe, but there are sometimes no power laws, and so, okay, that's just one example. But I would say in a more general sense, when we set out on a scientific project, we usually have some particular goals in mind, right? There's some particular things that we're hoping to accomplish, or observe, or discover, or answer. But then when you get into the act of performing science, right, where we be it theoretical, computational, or experimental, don't be so fixated on the initial question that you might not discover something, right? Because there are things to be discovered that are completely outside the realm of what you imagine your system is going to do, okay? But, okay, and I know this is extremely difficult because it goes against human nature to a certain extent to see something you did not expect, right? We usually tend to ignore things we don't expect, right? And I guess there's probably a lot of anecdotal evidence that people are finding difficult. So try to get around that. How do you get around that? Okay, now that I've identified a problem, I'm not actually sure I can tell you how to fix that problem. Anybody have any ideas? Yeah.
Talk to other peers, other people, share, carefully, of course, bounce it off some experts.
And show them naive observations without telling them what it is, for instance. Right. So that still precludes us discovering something that no one has ever imagined. Huh. All right, well, you guys can ponder that, I guess, as a homework problem in scientific psychology. Let me know if you come up with a really good solution. All right, I think that, all right, this could be an emergency. Could you guys give me 30 seconds?
Yeah, sure.
Axel, it's an emergency. No, I'm just, go ahead. Yeah? Oh, it's open to the air? Oh, okay. Okay, well, we'll have to work that through. It's not something,
Where the
at least nothing's on fire, so. But I'm giving a lecture for the next hour, so you know. Sorry, it's an unusual day. I ordinarily would never answer a phone call during a lecture. My apologies. Huh? No, it's a mechanical issue that we did not expect. Okay, so it's not it is not an emergency. You know, I got notes, so it's just, all right. Well, I kind of derailed you for a second there. All right, good. So I think that exhausts number one finally, and I hope those things are a little bit useful to think about. Now, so the rest of the talk, I'm going to be discussing MHD flows, MHD turbulence, and quantum turbulence. And I thought that a good way to start that discussion. There's the drums again. All right, we got drums on the brain. So I thought a good way of starting that discussion would be to play a few sounds that I've not already played to give you a sense of some of the things that can happen in MHD and plasmas. Okay. Let's see. Which one do we got? Oh, this one. Good. Okay. So magnetohydrodynamics is sometimes a good approximation used to understand plasma dynamics, which involves magnetic fields and a flowing material. It's actually a pretty good approximation for liquid metal flows. So there are many things that happen in plasma physics that are curious. And so I want to play you some sounds coming from Saturn when the Cassini aircraft was nearby. Okay, there's the power spectrum. Can you hear that? Everybody's suitably freaked out at this point.
Is this real time?
No, this is Cassini passed Saturn like 5 years ago.
No, I meant.
Sorry. Actually, I don't know. Maybe not.
They give you experiments at night, late night, dark room, awful sounds.
So these are thought to be different sort of plasma waves in the Saturn's magnetosphere. Yes, please.
So this is, how are we to interpret this measurement? Is this like a
These are actually electromagnetic waves being picked up by the satellite then being turned into the audio electronically.
And then what's the instrument though? Is it the signal?
I think this may be magnetic field.
Okay, so it's like some coil.
It's either magnetic field or electric field. The two would be coupled because these are actually electromagnetic, very low frequency electromagnetic waves going through space. Okay, so that was freak audience out number one. And let's see, so that was the eerie sound. How about, you guys ready for the bizarre sound?
Do you know if that was basically with the probe going fast compared to the dynamics of the magnetosphere, or was it vice versa, where the probe is essentially stationary and the magneto?
I'm sure the waves are going faster than the probe. The probe's going at a pretty good clip. But these waves are coming in. These are at the speed of light. So
Right.
the scene's
But
going on slower.
I'm talking about their dynamics.
Yeah. So I think that you're not hearing the dynamics locally. You're sensing the RF being emitted out of the dynamics that are happening elsewhere. And actually, a good example of that is when lightning strikes, it launches an electromagnetic wave in the Earth ionosphere cavity, and those radiate out at about 5 to 8 kilohertz, depending on time of day. And so 1,000 kilometers out, you can set up a loop antenna, and you can hear lightning 1,000 miles out at 5 kilohertz. So think of that kind of analogy as this. There's some stuff happening in the ionosphere and magnetosphere of Saturn that are making a radio frequency wave that are then coming to the satellite. It's kind of strange, isn't it? We live in a strange and wonderful universe, for sure. All right, so this next one is going to be data that Enrico took 12 days ago, give or take. It's a Saturday before last. So we have a summer undergraduate, Patrick McDonough, and Patrick's job was to try to see if a microphone would survive in superfluid helium. The goal was we hoped to hear reconnection of quantized vortices in the helium. So this is the probe did survive. This is a MEMS microphone of the sort used in cell phones. And this recording then we're going to go down through the superfluid transition from above. So to start with, you'll hear boiling, and then we'll go down through transition, things will become somewhat quieter, and then there'll be some other sounds. Which I hesitate to say what they are, because I don't really know what they are. So this is boiling. Sounds like boiling. Take 20 seconds to transition. Still boiling. And always you can see a cessation of boiling at the transition. That's a very standard feature. 10 seconds to transition. Can you hear that?
What was he listening to when he was taking the measurement?
All right, that's probably enough of that. I have no idea what most of those sounds are. I don't know. We're working on it. But okay, so those are cases of sounds coming out of a plasma system being dominated by some sort of magnetic field interaction with the plasma. MHD is a simple model of that. And the other then were sounds coming out of a quantum fluid. And so those are the things that I wanted to talk about. And I have some slides I'm going to show. But before doing that, I thought that it would be useful to actually show you the equations of MHD at a lower speed than Anik did, in a way that you could probably understand what they are term by term, more or less. So let's go ahead and do that. So magnetohydrodynamics is the augmentation of hydrodynamics when you have a conducting fluid that then can carry currents. And those currents can then be dynamically interacting. And the equations of MHD are the Navier-Stokes, but we'll need to know what equations the magnetic field is going to be governed by, and then what is the magnetic field doing to Navier-Stokes. So Helmholtz theorem says that any vector field can be specified by specifying the divergence and the curl of that vector field. And of course, we use this in electrodynamics, so we're going to use it here. I might just remark, though, that in the context of Navier-Stokes, we always couple the Navier-Stokes equation with some condition on the divergence, which often is 0. So actually, Navier-Stokes and the incompressibility condition are an equation for the divergence, and the Navier-Stokes equation is the equation for the curl. It just doesn't say, it doesn't look like an equation for a curl, but it is. It's actually telling you what you don't know after you know that del dot u is equal to 0. It's telling you what the vorticity is doing. Now, for the equations of MHD, then we're going to need something for the magnetic field. And the basic starting place is electrodynamics. So electrodynamics, of course, specifies for us what the divergence of E and the curl of E are. And it specifies what the divergence of B and the curl of B are. Right? And so depending on how recently you took and or taught this class, you might remember what all those terms are, but the divergence of E is sourced by charge, with a constant to get the units right. The curl of E is governed by induction. So if magnetic fields are time varying, you get EMFs, you get electric fields on closed paths. And the divergence of B would be non-zero if magnetic monopoles exist. But the only observation of a magnetic monopole, just to disagree with the speaker earlier in the week, was on Valentine's Day 1982 at Stanford University. And there's actually a PRL published showing their monopole pass through the detector, having 1 Dirac charge worth of magnetic charge. But in the intervening then close to 30 years, with many people having many detectors with larger cross-sectional area, no one's ever seen another one. Okay, so we will take as an effective theory that there do not exist magnetic monopoles, or if they do exist, they're so rare that they're not going to be relevant for what we're talking about. So you guys should go find that paper. It's kind of an interesting historical thing. Think about how frustrating that would be to the experimentalists. You see your monopole and no one ever sees it again. Because that's definitely a Nobel Prize winning event. Were it to be reproducible. Well. Now, the curl of B, of course, is driven by currents, generally, but then if things are moving rapidly, you also get displacement currents, and those are, of course, allow electromagnetic waves. Without that term, you can't get a wave equation out of Maxwell's equations. Now, in the context of MHD, we're going to consider that everything's moving so slowly that we're not going to be considering anything like the speed of light as being relevant, and we're not going to be having electromagnetic waves propagating through our liquid metal. Okay, so in some band, that's going to be fine. X-rays, in fact, liquid metals are transparent to X-rays, so it wouldn't be good if you considered those frequencies. But metals are pretty opaque to radio waves, for instance. Okay. Now in a plasma, then you have to just be careful and think carefully about, well, is it transparent or opaque or not? Okay, but MHD assumes that. So also, we're going to assume that there's no free charge. And that's generally the case for metals, that you don't have isolated free charges in the middle of a metal, because if you did, they're mobile, okay, that's what metals are, and they would move to the edge of the metal. So you can charge up a piece of metal, but none of the charge resides on the interior, all the charge resides on the surface. And I can work through a proof for you for that, but it's a basic electrostatics fact, actually. And plasmas tend to do the same thing, depending on the time scale, although you can have charged plasmas. So this is a limited theory for plasmas, but it's a starting point people do use. Okay, questions so far? Okay, now this is not enough to derive MHD. The extra thing you need actually is Ohm's law. And Ohm's law then gives you a recipe for knowing how J is going to behave in the presence of electric fields. Okay, so now I've not ruled out electric fields, I've just ruled out free charge. Okay? And in particular then, we're going to have causally significant electric fields coming out of induction. So I'm going to write down Ohm's law in microscopic form that says the current density is equal to the conductivity times the electric field, and then there's a term which is dual to Faraday induction under special theory of relativity. So if you go into a moving reference frame, you have effectively electric fields being caused by the boosts of the magnetic fields. It's probably usually described differently than that, isn't it? That's my best understanding of why that term's there, though. It's a consequence of special relativity. Even at low speed, you have V cross B terms that look like effective electric fields and cause induction in some sense. It's a second type of induction. Okay, now with all of that in place then, we're ready to get an equation for the time evolution of the magnetic field. And usually the way that's done is by taking the curl of Ohm's law. Okay? So go ahead and take the curl of Ohm's law and get the curl of J is equal to sigma curl E plus the curl of V cross B. Okay, but the curl of E is minus dB dt. So in fact, we've now arrived at an equation for the time evolution of the magnetic field. Okay, so that's one thing we're going to do. So we're going to make this sigma minus dB dt, and the curl of J is 1 over mu naught, the curl of B, right? Okay, so I guess we'll just go ahead and do this. So we've got 1 over mu naught, the curl of J, oh sorry, B, that should be, is equal to minus sigma dB dt plus that thing. Okay, so far so good? Okay, so now I'm going to move minus dB dt to the other side of the equation so it's positive. I'm going to realize that the curl of B is minus Laplacian B. There would be another term if the divergence of B were non-zero, but that's just that one term that survives. And so then I end up with dB dt. Okay, well I'm going to divide through by sigma also. dB dt is equal to the curl of, oh I made an algebraic error here. No one caught.
Sigma.
Yeah, we're going to need that sigma. Okay, so I'm going to divide through by sigma, so the only sigmas will occur over on that term when we're done. So the curl of B cross B plus 1 over sigma mu del squared B. Okay, so that's called the induction equation. And it's more or less all you need to know with boundary data to determine the time evolution of B in the presence of a velocity field. And it includes all of the induction effects. We've used both induction terms, if you will. The one in Maxwell's equations and the one in Ohm's law are adequately represented there. Okay, questions, comments? Okay, so we have a time evolution equation for the magnetic field. I guess that I want to point out that the curl of B cross B is equal to minus V dot grad B plus B dot grad V. And there'd be actually 2 additional terms if the divergence of V were not 0 and the divergence of B were not 0. It's just it's a vector identity. You can expand out that product. It's a product rule for curls, I guess. Okay, so far so good? So with that, then I can rewrite the induction equation in a way that may be somehow satisfying. It's dB dt plus V dot grad B equals V dot grad V plus eta del squared B, where I've just defined eta to be 1 over sigma mu naught. So that's the magnetic diffusivity. Because it really looks like a diffusivity, right? Because I've got a diffusion equation for the magnetic field with some coefficient out front. So it acts like a diffusivity. The magnetic field diffuses through metals. And they don't have to be flowing for that to be the case. You know, a piece of solid metal, if it's not ferromagnetic, you know, set aside that complication. You know, a big chunk of copper, if you put a magnetic field on it, impose it, and then turn off your imposed field, it takes a while for the field to diffuse out. And for instance, on our big system, if we impose a magnetic field on our big system and then turn off the external magnet, the decay time is 3 seconds for a magnetic field. And basically, of course, what happens is currents get spun up to try to preserve the magnetic field via Lenz's law. And you get induced fields that slow down. The field can't drop to 0 instantaneously. All right, now all of this has very good interpretation in some sense. So let's just go through it turn by turn. So time derivatives are caused by the advection of the magnetic field via the velocity field. So the velocity drags magnetic field lines, very literally. If I've got a field line, I've got a velocity transverse, those are going to tend to get advected with the velocity. It's an induction effect, really, but it's an important physical effect. There's a converse fact, which is that if you have gradients of the velocity field aligned with the magnetic field, then that can also cause time derivatives. In particular, I guess if I have a magnetic field like this, and I have a velocity field which above is going that way and below is going that way, this term turns out to be a positive number times b, and I've got dB dt is equal to a positive number times b. That configuration actually exponentially amplifies magnetic fields. So we call that stretching. You can stretch magnetic fields to make them more intense. And it's very much a conversion of mechanical energy into magnetic energy. And is part of why generators work, I suppose. But it's also probably why the Earth has a magnetic field. There's some sort of stretching with some folding. Unfortunately, this geometry can't sustain the magnetic field because it's also drawing it in from the side because they have to have velocity fields coming from outside. So as long as you have an infinite reservoir of magnetic field everywhere in space, you can keep growing like that, but that's kind of unrealistic. So if something more complicated has to happen. Okay, questions, comments? Okay, so now we have what is a good equation for the magnetic field. It's helpful for thinking about how that evolves. It can be simulated fairly readily. So then, the only thing we need to do is to modify the Navier-Stokes equation, because right now we have a velocity field that interacts with the magnetic field, but as of now, the velocity field doesn't know the magnetic field's existence. And that's very aphysical. If I'm going to be converting magnetic energy, or mechanical energy to magnetic energy, I'd best be reducing my mechanical energy somehow, so that these equations are conserve both momentum and energy in total. So that term actually has a corresponding term that has to go back in the Navier-Stokes equation for us to be done. So dB dt plus v dot grad v equals minus 1 over rho grad p plus nu del squared v plus, we need another force, although there's a force per unit density, of course, in this equation. We need another force that will then allow the magnetic field to back react on the velocity field. So what is the name of that force? It's not John. That was a really bad hand, wasn't it? Any guesses? What electromagnetic force causes a mechanical force on materials? Lorentz force, exactly. So there's only one good answer to that. And of course, that's the one extra equation you need to, well, I guess the Lorentz force is in Ohm's law in some sort of first order response theory way. But Lorentz force, you probably recall, is J cross B. And so we need a force per unit density, so we'll just put in a force per unit density, J cross B. Okay, so then equations 1 and 2 form what are called resistive MHD equations. And of course, I may have said this, but MHD is magneto hydrodynamics, which I'm pretty positive is a word that came over from Russian to English, because I think that the Russian theorists were working on this before anybody else. Do we have any native Russian speakers? Do you know what it is by any chance? And or just can you directly translate it? What would it be? So say again?
We need to get the Dynamo.
Okay, right. So there it is. So the thing about MHD equations is that they're simple. They're simple at the level of Navier-Stokes. They're a good model. It can be computed in many cases. There's a lot of analysis that can be done on them, but they're not the only model. They're not the only theory. Especially for plasmas. And although they actually do a remarkably good job for liquid metals, but liquid metals are a very simple sort of plasma, if you will, because almost all the momentum is carried by the ions, and almost all the current is carried by the electrons, and you don't have to worry about the electric current being carried by the ions, and you don't have to worry about the momentum being carried by the electrons. So, and they remain relatively charge neutral. So those are all very simplifying assumptions that many plasma systems lack. And so in plasmas, a lot of times you can find cases where MHD you're well beyond the MHD regime, and you might have to put back things like things going near the speed of light. You might have to independently model the ions and the electrons as separate momentum fields and separate current fields. And so the two fluid models are quite common in plasmas, where you separate your ions from your electrons. I guess, of course, in the context of Navier-Stokes, we're also assuming near local thermodynamic equilibrium, except for some mild velocities and pressure differences. But in a plasma, that's often not correct, that the probability distributions of ion velocities can become non-thermal pretty quickly in many simple physical applications. So in that context, then, you got to actually model the entire, what sort of theory would that be? It's a kinetic theory, I guess, where you have probability distributions of velocities, and at one point in space, you have a population of velocities, and things get kind of complicated.
The problem there will be it will not relax to any, it will not relax, so it will, I don't know how to do this.
The solar corona is not in thermal equilibrium, for instance. So, you know, that you have to work harder in some plasma context. Yeah, I don't know what to say about our alien friends in Saturn, whether they're in thermal equilibrium or not. Quite depends on where you are in the magnetosphere or ionosphere. Okay, so good. And okay, so the last point I wanted to make about these equations is that this term allows a back reaction and a saturation of growing magnetic fields. So let me just say a little bit something about growing magnetic fields. It's one of the aims of a number of different laboratory experiments to explore dynamo action. If I have the induction equation, which I'll just make it more compact for that. If I have the induction equation and I fix the velocity field, okay, which you can do time dependent or you can do time stationary, there are variations of this. That is a certain class of problems to try to understand the initial growth of the magnetic field in a system that may become unstable to dynamo action. And so this is called the kinematic dynamo problem. And it received a lot of historical attention. It would be an entire lecture in itself to give you all that. But for early times of the theory, people thought that this equation alone would describe dynamo action. You get instabilities. And then there were a bunch of theorems proven by Cowling of flow geometries that could not give dynamo action. Entire classes of flow geometries with too much symmetry. And so for a while, people started doubting you could get dynamos out of these. And then people actually exhibited numerical dynamos for systems lacking the symmetries that Cowling said you could not have. And now everybody believes that this essentially governs instabilities to growing magnetic fields, at least in the context of liquid metals. And so if I actually fix V to be time independent, then this is a linear equation. Well, what are not time independent? It's a linear equation in B. And if V does not depend on time, then it can be solved using separation of variables to obtain a time dependence, which is exponential. So in the context of stationary V, then, we have magnetic fields that grow along particular eigendirections exponentially in time. And of course, you have to sum those up and project them on initial condition for it to work. So really, then it comes down to an applied math question: is does the right-hand side of the equation, does that operator possess positive eigenvalues? And that will depend on the magnetic Reynolds number. So you've probably seen the Navier-Stokes written with, instead of nu, it's 1 over Reynolds number. Has that cropped up in the last 2 weeks? Okay. Similarly, I can write this where here I will have 1 over the magnetic Reynolds number, and that then becomes the small parameter where if I make that parameter small enough, you might hope to get positive eigenvalues, and indeed you can for simple flow geometries. And at least 2 experiments, one in Karlsruhe, Germany, and Riga, Latvia, showed kinematic dynamos that they had calculated before they had done the experiment. There's an experiment in Cadarache, France that also showed dynamo action, but it did not show the eigenfunction that they calculated from their flow field, which was a little bit disturbing to them and those around them. But they also put ferromagnetic disks on either end, and those seem to be causally significant in there. So this has no ferromagnetism, I should just make it clear. So if you have ferromagnetic particles or liquids or boundaries, you have to have an augmented theory. You get gain out of ferromagnetism for sure, as well as residual flows. Okay, questions about dynamo action? Everybody ready to go build a planet? Okay. All right, so I think we probably are done. Yeah, we're done with 3. Now, there was one thing I wanted to do for you, which I calculated this morning. Okay, so warning, the following calculation may have errors in it. So Anik spoke about turbulence in the context where you have waves, and she had 2 specific examples. Waves from rotation, which are inertial modes, restored by Coriolis and pressure. But she also talked about waves in the context of MHD, which were Alfvén waves. Okay? So I thought I'd just actually drive for you in 6 or 8 lines that there is a wave equation lurking in here, which are Alfvén waves. Does that seem helpful? Okay, so I think I've done that already in slides for the inertial waves, which is just getting rid of everything except time dependence, Coriolis, and pressure. You quickly arrive at a wave equation. Okay, oh gosh, maybe I shouldn't erase that. Okay, so didn't get far erasing it, which is good. So this is J cross B. I'm going to go ahead and call this the curl of B cross B. And I snuck in one of a mu naught, which is our exchange factor between J's and curls of B's. Okay, so we're going to take that equation, and we're going to take the equation here. Okay, well, let me rewrite that one so they're all together. Right, so this is then our resistive MHD context. I'm going to go ahead and use the breaking out the advection and stretching terms. And then we've got a distributive term. Yeah, boy, you can really tell experimentals from theorists. I guess I've used all dimensional equations today so far. And all in SI too, so it's even unit specific. How very nitty gritty, huh? Oh, well. All right, so in the context of Alfvén waves, what we say is that we have a strong existing magnetic field. Alfvén waves arise in the presence of a strong background field. So I'm going to say B is actually some V naught, which is pretty big. Actually, I'm going to call it V naught Z patch to make my life a little simpler. Plus a disturbance, which is somehow small. Right, that's going to be vector. Okay, and really then, these wave motions come about, of course, by some restoring force. In the case of inertial waves, the background vorticity of the fluid has something almost like a line tension. And so if you get a fluid uniformly rotating and you pluck it, the line tension of the background vorticity sends waves out. Although they're centered out in cones, so it's really kind of strange, but fine. Okay. The same thing can be said for magnetic fields. Magnetic fields have a line tension. And that really just comes down to the fact that if you really think about the approximation of a magnetic field line, which is, you know, conceptually useful, although only true in Type 2 superconductors. Is the magnetic field quantized in the vacuum? Sorry. If you think about a uniform background magnetic field, if I pluck the magnetic field lines, they have a line tension and they will launch waves. Those are Alfvén waves. Okay? Although you have to have matter present because the velocity field is participating. So in particular, in addition to this, we're going to have a velocity disturbance. So V is going to be just V prime. It's going to be the disturbed field. There's no background velocity. Of course, in the case of the vacuum, if you plug a magnetic field, you'll launch electromagnetic waves. But we've ruled these out. We're going to end up with these slow waves. They're actually motions of the mass. And physically, the idea is that if I move the magnetic field because of induction, the velocity moves with it, and then it wants to be restored back to its original position. And so then you get transverse velocity motions to get coupled with transverse magnetic fields. And they propagate along the field line direction. So in fact, probably some of the things we were hearing in Saturn were associated with Alfvén waves, which is a very good possibility. Now, so things are small, and so we're going to have to make some choices. I'm going to go ahead and just make some choices for us to make life simpler and simpler. Okay, so we're going to need both of these for sure, and we're going to need then some way of a background magnetic field interacting with a perturbed magnetic field. So we're going to need that one, and I guess we're going to need time to. So I don't think we need both of those. And of course, the thing we have big is a big magnetic field, right? So, but it has no gradients. So in fact, I'm pretty sure this term is going to be irrelevant, since our big field has no gradients. And it would only be perturbed velocity fields acting on perturbed magnetic fields, and that would be second order small. Okay? On the other hand, I can have a big magnetic field here. Okay? So having crossed out a whole bunch of terms, let me go ahead and put these in. So the background magnetic field has no time derivative, so I end up with a, so actually let's do the magnetic field. dV prime dt, and then I've got a B naught z hat dot grad v, so it's actually a B naught d by dz of v prime. Okay, so our induction equation simplified somewhat. like lots of surgery. And then the velocity field, so we've got the d prime dt is equal to, and then our background field has no curl, right? Because it's uniform. So that's going to be the perturbed field. So I'm going to end up with a curl of the perturbed field crossed into the background field. Oh yeah, so actually, right, and so actually let me just rewrite that one, taking a step sideways. We got dv prime dt is equal to, and the background field is actually b naught z hat, so I end up with a b naught over rho mu naught, the curl of b prime, cross z hat. Okay, so these two equations then together form a coupled system of linear PDEs which possess transverse propagating waves along the direction of B naught. And I think we can put those together relatively easily by taking the time derivative of one of those, and let's see, so which one will be easier? Yeah, so if I take a second time derivative of the magnetic field equation, I will get a time derivative. No, let's take a time derivative of the velocity one. We can do it either way because they're coupled in the end. What did I do in my notes here? Yeah, I guess, right, so I took a second time derivative. Right, so we'll take a second time derivative of the magnetic field. It doesn't really matter. So the second time derivative of v prime then is going to be b naught d by dz d by dt of v prime, but we know what d by dv prime dt is, so we'll just go ahead and insert that. So I end up with a b naught d by dt, d by dz, and then the right-hand side of what was the Navier-Stokes equation. Curl of b prime cross z. All right, well, it's not the world's most lovely wave equation, because it's not. It doesn't look like the equation for light propagating, because there's a preferred direction. So there's some geometry built into this. But what you notice is that there's some constants out in front here, right? So I've got second order in time. I've got two derivatives in space. So it does have kind of a wave equation feel. And of course, what the constants out front, generally speaking, would be the speed of the wave squared, right? Which is the case. So b naught squared over rho mu naught is defined to be what we call the Alfvén velocity. And I'm not certain at this point if that's how Alfvén is spelled actually. The P or F? F?
Yeah.
Sorry. And there's probably some sort of accent on it that would be too. I see. Yeah, please.
Comment. If you just cancel the pressure term, you are actually making the fluid compressible. So the
So,
better way would be probably projecting it out on the space perpendicular to the gradient or something.
right, but I guess that as long as I assure that V prime and B prime are incompressible, I'm not generating any compression from the nonlinear term since I've zeroed it out entirely.
That will not change surely the.
Yeah, so in fact, you can get combined acoustic and magnetic waves if you do a lack of compressibility, but yeah, I may have been too quick to cancel that one out, quite possibly. Okay, so in any case, so these alpha waves then play a pretty significant role whenever you have a conducting material such that the viscosity is low and the magnetic diffusivity is low, so that these waves don't get greatly damped. And there's a dimensional screw for that, of course. If you form a magnetic Reynolds number from the alphane velocity, this is called the Lundquist number, which we'll call M sub L. Now you notice this is a magnetic Reynolds number in some sense, but using the alphane velocity. It turns out in astrophysics, usually when the astrophysicists say magnetic Reynolds number, they mean that. So just beware that different communities use slightly different words for the dimensional screws. But the Lundquist number is actually the quality factor of alphane waves in most situations. So if that gets high, everything gets relatively wavy. Yes, please.
Also, to come back to that, I didn't get why you can spread the signal to space. Why you can suppress, what was your assumption to suppress the signal in space?
Okay, so I'm assuming that the dissipative mechanisms are small to uncover the neutral wave modes. We can then go back and include those dissipative terms and you discover damped waves. And so instead of real frequencies, you'd have complex frequencies. And that's, I think, a relatively straightforward exercise for what will end up being linear plane waves. Because those linear plane waves will still be operators of the diffusion equation. Or, exactly. Right, I was mainly aiming for the alphane velocity, to tell you the truth. Yeah.
What's setting the scale L?
Oh, the size of the box? Which makes sense, actually, if you've got a big tub of sodium. So in what sense, then, is Cassini going to be able to define a Lundquist number for Saturnian chirpers? I'm not sure. But, you know, a magnetosphere has a size, I suppose. Or if they have things happening in an ionosphere, that has a definite sizes. So it's going to be very problem-specific, I would guess. Right? But it is, you know, these sizes, in some sense, then, from upstairs here, the large scales over which these waves are most happening. So this could be, the Lundquist number depends on the wave number or wavelength of the particular alphane wave you're dealing with. Because that's going to tell you how much damping you get for that alphane wave, depending on its wavelength. That'll be the characteristic length for the setting the decay. Okay, questions, comments? Yes, please.
Will you find the alpha velocity? Still be the square root of that?
Oh, no, actually, yes. Thanks. No, that's very important. Right.
So why don't you replace this F by F and a B? Just to get that right.
Thank you very much. Now, didn't I caution everybody on Wednesday you're supposed to ignore it? Well, for names it's worse in some sense, right? Because it's a real person doing this.
Just if somebody wants to Google the names.
Yeah.
They can find
Yeah.
it.
Right. Okay, other comments or questions about this? And if I could just say, so the general context of this, when you have turbulence, if you have a strong enough magnetic field, or if you have strong enough rotation relative to viscosity, everything's going to become very, very wavy. And trust me, it becomes very, very wavy in nature and laboratory experiments in those conditions. Yes, please.
I'm sorry, yeah, the astrophysicists, they call that the magnetic Reynolds number.
Yes, sir.
Where is, if at all, the magnetic Reynolds number in our?
Okay, so if I were to make this equation dimensionless, this would be 1 over the magnetic Reynolds number. Instead of the diffusivity, right? So Rm is just like the Reynolds number, but it uses the magnetic diffusivity. And so then you have a 1 over Rm here. And it kind of plays a similar role in this equation that 1 over Reynolds number plays in Navier-Stokes, that when the magnetic Reynolds number gets big, the magnetic field has finer scale structures, but it's also capable of magnetic instabilities at large magnetic Reynolds number. And in particular then in the Dynamo problem, If you have a linear instability, there'll be a critical magnetic Reynolds number. If you exceed that critical magnetic Reynolds number, you'll start growing the magnetic field. That eventually then saturates via the Lorentz force, back reacting on the velocity field to change your velocity field such that you can no longer grow. And that's kind of essential because there's only a finite amount of energy available, so your magnetic field cannot grow exponentially indefinitely, clearly. Okay? Yeah, 3 took a little while, didn't it? But it's useful sort of general background knowledge. So I think probably we'll be able to go over now. And so I wanted to talk about both MHD phenomena and reconnection, and also quantum turbulence and reconnection. And they're in the context, in the first case, of these equations that we've done. But I'd like to make an analogy between these two situations, because I think that to a certain extent it's fruitful to think about the analogy, although it's imperfect because the order of the fields is a little different. But they do share some similarities. So we're going to talk about MHD turbulence or plasma turbulence and the role of reconnection. Reconnection refers to magnetic field lines that come in and exchange tails. So you can have, it's quite common in astrophysical settings to have bundles of magnetic field lines with plasmas running through them. And you can see that in the solar corona very readily, that you get these arcs. Oh yeah, in fact, I should have prepared it, but there's this, if you Google the Bastille Day slinky, since yesterday was Bastille Day, that actually was a family of arcs forming a prominence across the sun during last solar max. It's really quite beautiful phenomena. But, so it's quite common to have these arcs of magnetic field lines with currents running along them. If they interact, they can then exchange tails. They can change their topology. So that's called magnetic reconnection. Similarly, in quantum turbulence, we have quantized vortices that can also interact and exchange tails. And there's some interesting analogies between those two that we'll get to. And yeah, well, fine, good, okay. The plasma turbulence is non-topological, unlike our quantum turbulence, so that's one distinct difference. It's an impure, yeah, some pictures of people. I don't know. I guess I should say, the National Science Foundation has been very, very good to me, allowing me to do these things. I don't know why they allow me to do these things. Okay, fine. Now, there's a lot of magnetic energy generated, and essentially, I argued on Monday, almost every astrophysical object has a magnetic field. So you look at the sun, look at galaxies, look at the Earth, almost all planets have active magnetic fields. All stars that I'm aware of have active magnetic fields. So the only 2 planets that don't have active magnetic fields in our solar system are Venus and Mars. And there's lots of debate as to why they don't, but all the rest do. Oh, I don't know Pluto. Oh, Pluto's not a planet. Okay, good. It's still true. Now, magnetic energy is generated, but in fact, it's a difficult problem in thinking about magnetic energy to find out how it's dissipated. And the problem is that the magnetic Reynolds numbers that you can calculate for most astrophysical situations are astronomically large. And that makes it then problematic to try to figure out how you can actually get rid of magnetic energy. It's really an analogous problem to the problem of dissipating energy in turbulence, that if the viscosity becomes vanishingly small, the naive guess is you don't have any dissipation. Okay, and of course everybody's dissuaded of that fact now. So in the case of magnetic energy, the theory is not as far along developed as we have for K41. In part because our observations are not as good of small scales that are happening because they're all remote. So we don't live in a plasma or a liquid metal, and you can arrange them in the lab, but it's challenging. So we have imperfect knowledge about dissipation, and the problem is that if you set the magnetic diffusivity equal to 0, the magnetic field is frozen in to your liquid and actually becomes a topological object. So you can't cross magnetic field lines in the ideal limit. Okay, now a little Nigel in the back of my head is saying, yes, Dad, but the limit of eta going to 0 is not the same as eta going to 0. Yes, Nigel, I agree entirely, but we still don't understand that limit. Okay, so there's work to be done. Am I actually completely insane? Hey, I could have worse people talking to me in the back of my head, right? Nigel's all I have to carry around. I guess I'm good to go for right now. Oh, gosh, I don't know why you guys put up with this. So there's this release of magnetic energy is important, but actually also ends up being often explosive. So actually look at the magnetic energy in the sun. When the sun decides to dissipate magnetic energy, it does it by ejecting coronal mass ejections with enormous amounts of mass, or flares, or prominences, or it's all pretty violent. And people are not entirely sure why. If you look at this, the energy spectrum of particles coming from the sun, they're very broad. So the stuff that's being spit out, particles that are escaping the magnetic fields, have a very broad spectrum. The cosmic ray spectrum is also very broad. So I think I showed some. So this is one of my favorite movies. We'll play it a couple times. So this is a prominence that arced up in the sun, kind of twisted about, interacted with itself. Gosh, isn't it beautiful? That prominence is probably about 5 Earth diameters across. Okay, so this is relatively large, quite hot object. So these are magnetic field lines. If you're actually seeing the magnetic field lines, they'll also have currents flowing along them. You know, charged particles have to spiral along magnetic field lines. And so this is actually more or less lightning on the sun. Give me just a second. If you have a magnetic field line exiting the solar photosphere and entering somewhere else, and if the electric potential gets high enough between those two spots, it discharges along the magnetic field line. That's what these arcs are. So they are this plasma limit of what we have lightning on Earth. And the currents are astrophysical, of course. The currents are quite large. Large amount of energy is being flown around here. Yeah, please.
So you notice the CCD gets all this noise. Is that coming from the sun?
You're a keen observer. Okay, so let's everybody look at that for a minute. Look at the development and the noise.
Yeah.
Right. Okay, so what's happening is that there's reconnection happening in this. This is more than one arc. The arcs are colliding with each other. They're releasing magnetic energy, and as best I can understand, that causes a spray of charged particle radiation coming out from the sun. Those charged particles, which are mostly protons, honestly, hit the CCD and register as light. And actually, if you get the wrong satellite in the wrong place at the wrong time, it'll just zort your satellite. Yeah, please.
I've always wondered, I mean, I've always been impressed by these images, but do they, I mean, they just happen to get this beautiful one there, and I'm sure that...
They're looking all the time.
Yeah, I was wondering, are there cameras set at different parts of the photosphere, just all the time waiting?
Okay, so this is from the TRACE satellite, actually, and is up there just looking at the sun all the time. There are a whole bunch of different satellites. So this is actually, if you Google Solar Cycle 24, you'll actually get a ham radio operator that has a website. And you can, for instance, you can see the X-ray flux right now. So we don't have a lot of flares going on. So this is now, okay? And so you can get sort of nowcast of solar weather if you're into that sort of thing. A lot of this is driven then by the sunspots. So this is a magnetogram, and sunspots that are patches of inward and outward going magnetic field, and around them is tend to where you get bad space weather. So the sun's magnetic field reverses like the Earth's, but does so periodically. And the sunspot cycle is also periodic and varies with that. So solar max was around 2001. We had a very deep solar minimum for the last couple of years, and we're coming out of solar minimum. So this is a forecast for a solar max occurring around 2013. This is a sunspot number. And it's been observed for hundreds of years, actually. It's relatively easy to see sunspots with the right sort of gear to keep from blinding yourself. Okay, so space weather is kind of interesting. Now, so this sort of phenomena, then I would say, okay, we've got some various astrophysical phenomena. Well, let me go ahead and play this movie because it's pedagogically useful. So the Earth's magnetic field inflates a bubble around the Earth called the magnetosphere. It's really a magnetic field of the Earth and the Earth plasma dominating over the sun's magnetic field. There's a bow shock and a magnetotail, so it's a sort of tadpole-shaped thing. So there's the sun, and it's spraying all sorts of nasties at us. Of course, light goes through. The charged particles actually tend to go around the magnetosphere, so it shields us substantially from a lot of the charged particle radiation, as long as you don't fly outside the magnetosphere. So if one of you were to be the first person to fly to Mars, and you get outside the Earth's magnetosphere, and you have a bad solar storm, you best don your lead undies and or crawl into a lead box pretty quickly, because the stuff will actually just kill you straight away in a bad storm. It's fairly dangerous. I should say that actually the images of the prominences and this animation were all done by the Trace Soho collaboration. So Trace Satellite's one of the solar observers. Really fantastic stuff. Now, there are intense currents that happen in the magnetosphere at the bow shock and the magnetotail. They're not stationary in time, but they're part of the ongoing space weather. Those are the places where you get very strong magnetic reconnection. In the bow shock, you get reconnection between the solar magnetic field and the Earth's magnetic field. In the magnetotail, then, well, so things are sort of sweeping around and occasionally slap together back there. And you get again, intense currents that have been studied by satellites a great deal down in the magnetotail. Okay, I think that maybe all I was going to say right now about some of the MHD phenomena. Well, I think we're going to come back to magnetic reconnection in a bit. Any questions or comments? Okay, I know I'm giving you more general knowledge. Now, we already talked about superfluid helium, which we get by cooling down below the Lamb transition, helium-4 in this case. And I'm going to try to make some analogies to some of the things that happen in space plasmas and in superfluid helium. Okay, so I believe we already talked about the fact that you get an order parameter, that the velocity of the superfluid is the gradient of the phase, with the proportionality constant being the quantum of circulation, Planck's constant divided by the mass of the helium-4 atom. So that context, whenever you have a complex field, they can admit phase singularities, which are just places where the amplitude of the complex field is forced to zero, and you have a 2 pi or multiple winding of the phase. Since 2 pi, of course, is you come back and it's the same phase. It's ambiguous up to factors of 2 pi. So these are quantized vortices. They're little quantum tornadoes that are mobile in the superfluid. A interesting, useful model for the motion of the order parameter is the nonlinear Schrodinger equation, or the Gross-Pitievsky equation, that both Cecilia and David have spent a fair amount of time looking at solutions of those. Dave, there's Dave. Dave, sorry. I'm supposed to stop calling you Dave. Okay, now we got it on camera. So this equation is actually the linear Schrodinger equation plus a cubic term that forces the amplitude of the order parameter to a constant value almost everywhere. It shows that you have a condensate. Okay, but it actually admits quantized vortices. One of the things about this equation, though, is that small disturbances on a flat solution, so you have one time derivative here and two state base derivatives, small disturbances can behave at short length scales with a dispersion relation, which is quadratic. And this is physically significant in the model because it allows things to happen fast on small time scales. Okay, and this is going to be important in bringing it back to some of the space phenomena, so that's the reason I'm pulling that out. So what is quantum turbulence? An evolving set of quantized vortices, aperiodic, a large range of length and time scales. We have quantized vortex rings. They're vortices that can end at the wall generally, or they can form a ring out in the bulk. Those are the only two possibilities. They can't end in the fluid because of Stokes' theorem. You have circulation, none. It's just not an option for the complex field to do that. So quantum turbulence, as best we can observe, is really dominated by the reconnection of quantized vortices, which I'll define as some length and ring collapse, which is really simple. You got a ring, it's propagating, like all good smoke rings do, and it shrinks to zero due to some dissolutive mechanism. Okay, and I guess we also end up with a power law of distributions of velocities and energies in the quantum turbulence. Okay. So I already showed some of these solar prominences reconnecting that cause flares, and so these are not my figures, but from review papers talking about solar flares. So it's thought that if you have one of these coronal loops, it can rise up and actually, if you get a twist in it, it can reconnect with itself. And that then is carrying energy out away from the sun, because now I've got this bubble of current and magnetic energy which has left the sun. Right? It's become disconnected from the photosphere dynamics. Okay, and really the analogy would be if you have a lightning strike that went around and hit the Earth, and then the lightning strike formed an elongated arc and twisted around and formed a loop. Oh, sounds kind of like ball lightning to me. No one knows quite sure what ball lightning is, though. But okay, we'll leave that aside. Ball lightning is kind of interesting. Yeah, so flares come out of these events. That's one place then reconnection is very well established is in the solar corona. It's just, you can see it. And it almost always sprays a large amount of energy out into space, sometimes also carrying a fair amount of mass out as well. Good question?
Yeah, I mean, so these reconnection events must involve some sort of singularity, right, with the vorticity?
So the mechanism for reconnection in a space plasma is a controversial subject. And there are several people that all think they know what the right answer is, but they are believing different things. Okay, so I'm going to give you a particular point of view, which is work done by one of my colleagues at Maryland, Jim Drake, as to what allows that to happen. But yes, there are near singularities that are involved in this. So I guess reconnection has also been observed out in space, not near a planet or the sun. The solar system is filled with a diffuse plasma, which is also relatively magnetized. It's also blowing out from the sun at 400 to 600 kilometers per second. Actually, that solar weather will give you the speed right now of the solar wind, but it's usually coming out at a pretty good clip. These magnetic field geometries out in space actually turn out to be very complicated. The sun is spitting out a complex pattern of magnetic fields all the time. And using satellite missions, people have seen what is expected to be a signature of a reconnecting sheets of magnetized plasma. Okay, so another example where this has been observed in space, the mechanism again is controversial, so people spend a lot of time building space hardware to go look at these things in the geotail or the bow shock or outside the magnetosphere. It's a very active area of research. Oh, okay, X-rays is fine. Okay, now, so to get magnetic reconnection then, the picture could be something like this. The lines here are magnetic field lines. And so what you really need to have is some sort of compressional velocity field that brings opposite magnetic field lines together. Now, the problem is, of course, is that if they're frozen in to the fluid, they can come close to each other, but they can't actually reconnect. What we want them to do is to exchange tails and form these arcs. Okay? Now, dissipation can do that. If we let diffusivity be there, the field lines can diffuse together. Okay? But it limits then how fast the reconnection can happen, and everybody who's tried to estimate the speed of reconnection given the astrophysical diffusivities has said, no, you can't reconnect in the time scales of the events we see given the diffusivities we know. So those simple models are all wrong, but of course nobody's surprised that a simple diffusivity is maybe not all that's happening in a complicated flow situation, right? Right, so I think that this slide actually I think more or less has that right argument. Slow reconnection is not consistent with the observations. On the other hand, it turns out if we go beyond MHD for these two fluid models, it's often the case that in addition to all of the ohmic effects we've had and the other effects, that there are Hall terms. Right? The Hall effect is a standard thing in solid state whereby magnetic fields cause the ions and electrons or electrons and holes to move differently than each other in the presence of the same electric field. And it's thought in plasmas that a Hall effect might then give you an extra dispersive effect, which is not dissipative, it is kinematic, but in fact it can allow fast reconnection. It allows dispersive waves that could allow reconnection. And in particular, the most important point is if you look at these dispersive Hall waves, which I guess give rise to whistlers in the Earth's ionosphere. So I didn't. There are other sounds you can get that go, which are plasma waves. So the Hall effect can give you whistler waves readily in a planetary system, but they have a dispersion relation omega equals k, or omega proportional to k squared. So now do you know why they're whistlers, Grant? Well, so if omega equals k squared, the phase speed, omega over k, is linear in k, which means short wavelengths arrive at you before long wavelengths arrive at you. Which is true for Kelvin waves too. So Kelvin waves have a very similar dispersion relation along vortices. Okay, but that means short length scales can move very fast. Right? Their speed is only limited by how small they can get. And you can see why that could be useful then to rearranging things at small scale where diffusivity is unable to. And there's some simulations, well, a number of simulations that back that up, but we're getting close in time. So let me actually, I want to get back to the reconnection of quantized vortices, but one last point about the reconnection of these space plasmas. If I have a highly magnetized current, so I've got current flowing along a bundle of magnetic field lines, right, which you can see in the sun, and then I bring it into contact with another magnetic field bundle with current, there are two distinct possibilities of what can happen. The direction of the magnetic field line and the direction of the current can be independently chosen. This is the magnetic helicity, okay? In one case, after I reconnect, this current flows into the same sense of current in the other rope, okay? So this is the current parallel after reconnection. This is the happy case. Okay, we've got happy reconnection. The current of one just can keep flowing into the current of the other. Okay, but now if I reverse the current, but not the magnetic field line in one of the bundles, after the reconnection, I now have currents that are coming into this point and into this point from one side, and out of this point and out of this point on the other side. And so you get an accumulation of charge within those magnetized plasmas of each side, and you probably get a very rapid acceleration of charged particles escaping out of the magnetic fields. So I think that the sprays of magnetic fields that we see coming out of the solar corona, and this is a hypothesis which I am not entirely certain is correct, but I believe it's a good chance those charged particles are being liberated by these anti-current reconnection events, where you get a large charge accumulation of large electric fields and unhappy reconnection. Okay, nobody's quite sure where cosmic rays come from. Yeah, please.
Can we go back to the connection thing? So if the currents are anti-parallel, couldn't you end up with a reconnection such that you still have the...
Okay, so it's a good question. So it turns out that the magnetic field that's supporting these is not the magnetic field being caused by these currents. It's much stronger than the magnetic field being caused by these currents. Although that implies a sort of twist to the bundles. So the direction of reconnection is determined by the guide field. And the currents are along for the ride, and they're relatively ineffective at determining that direction. Right. Good question, though. Other questions? Okay, so the reconnection of quantized vortices is somewhat simpler. So I'm going to show you what that looks like just in a couple minutes. So, we put particles into superfluid helium. Enrico's put lots of particles into superfluid helium. And then we illuminate them with a laser sheet, very much like a standard PIV or a thin sheet particle tracking setup. We do particle tracking. We have a relatively expensive, low light, back thinned, intensified CCD camera from Princeton Instruments, which allows us to not have to put much light into the helium. And then we just watch the particles move. Yes, please.
When we learned about PIV, we learned that the density mismatches can potentially be important. And I would expect for helium, perhaps that's even more important. Is that something you guys heard from?
I'll let my charming graduate student Enrico answer that one. Enrico, what's the basic answer to that question?
The density of the particles.
Yeah.
So we use a hydrogen which is buoyant, but it depends on the size of the particle. The effect of the terminal velocity of the particle.
But very slightly buoyant.
Yeah, slightly buoyant.
So 10% mismatch? Right.
But
But very...
we use also a mixture of deuterium and hydrogen to have like completely buoyant, but we see that it's not a big deal, so we can use hydrogen.
And one of the things that Enrico's discovered, in fact, that you can use very badly mismatched particles if they're only 100 nanometers or so.
It's with the
Because then they're dust in the wind, right? Even if they can't settle out because their free fall velocities are too small. Okay. Okay, so we're going to look in the flow. So we produce particles by a technique that Greg Bewley invented. So Greg was working on his PhD from Yale under the supervision of K.R. Srinivasan while Srini was in Trieste, but working in my lab. So it's kind of a long, peculiar story. So we can get very nice particles. This is a mist of particles. You can see the mixing gradients. This is in normal helium. We can then cool that down below transition, and particles that find themselves near a quantized vortex get stuck. Okay, and there's a trapping mechanism which I won't elaborate on. But what happens then is that as we go down through transition, we start to see filament-like objects that appear in the flow, which are then some set of particles being trapped on the quantized vortices, or bundles of filaments. This is actually a big shock to the community when they first saw these movies. They've gotten used to it for sure. Okay, yeah, smaller is better, fewer is better. They're not entirely passive. Okay, I showed you counterflow last time. Okay, so Feynman in 1955 predicted that quantized vortices could reconnect, exchange tails. Well, he didn't use the word reconnection, But he said basically if the process from B to C is allowed, then you can dissipate vortex length more readily. Okay? And it was thought that this was possible, a lot of theoretical work done on it. Now in our case, we can't see the vortex cores. We have trapped particles on them. So at best, we might see something like this. Okay? Okay, so to look down here. Oh, not so slow. That's not good. Okay, give just a second. Yeah, this won't take too long. There's a better way to do this. And I will stop probably after this movie. Nope, not that one. Okay, yeah, this one. Okay, so here again is a field of hydrogen particles. Okay, so look here, and then up in here. Okay, so this was the first direct observation of the reconnection of quantized vortices, and it really very much had the character that you would expect. We were able to quantify quite a few things from this. But one of the things that it does is when you reconnect the quantized vortices, they have very large curvatures, and they move very rapidly out from the reconnection because of their line tension. So the velocity distributions tend to have power law tails, reminiscent of the power law tails we see in the charged particles being spewed out of the corona. Yes, please.
What is this real time?
Yeah, that's about a centimeter across. Right. Okay, so I think with that movie, I'll go ahead and stop. It's lunchtime, I expect. Yeah, that was really my favorite movie too, so not good one. Okay, any final questions? Okay, we can always ask me over lunch. So,